Hey guys, the most amazing thing about our universe is its size. It is unimaginably huge. But at the same time, this is also the most disappointing part. Just think about it. Even if today we use our most powerful telescopes and discover another Earth-like planet in some galaxy that could support human life, reaching it would take centuries. In fact, for any individual human, leaving our own galaxy is basically impossible. You already know that Earth is in the Milky Way galaxy, and the closest galaxy to it is the Andromeda galaxy, which is approximately 2.5 million light-years away from Earth. So if we try to travel there using a spacecraft, whose usual speed is around 28,000 kilometers per hour, it would take about 94.5 billion years to reach it. And even if somehow we develop technology to travel at the speed of light, it would still take 2.5 million years to get there. This is truly discouraging. What's the point of finding all these planets if we can never actually travel to them? But what if there was a shortcut, a way to travel outside our galaxy? A shortcut through which we could cover millions of light years in just a few months. That's where things start to get interesting. These shortcuts are called wormholes. The 2014 movie Interstellar is one of my favorite space movies, and it shows this idea really well. In the film, when Cooper and his team leave Earth in search of habitable planets, they travel from one galaxy to another through a wormhole in just a few minutes. According to the movie, this wormhole was discovered near the orbit of Saturn by NASA, and it plays a very important role in the story. But the most interesting part is that the concept of wormholes is not just science fiction, it is actually based on real science. To understand what wormholes really are and how we might use them, we first need to go back to Albert Einstein's theory of relativity. When Einstein developed this theory, he expressed it in the form of equations, known as the Einstein field equations. These were first publicly presented on the 25th of November 1915, when Einstein submitted his paper to the Prussian Academy of Sciences in Berlin. In total, these equations consist of 10 different nonlinear partial differential equations, although they can also be represented in a shorter single form. Don't worry, we won't go into the math details here, because the equation itself is extremely complex. If you expand it, the steps become so complicated that even someone who loves mathematics might feel overwhelmed. In simple terms, these equations tell us how matter and energy influence the curvature of spacetime. Einstein explained this idea with a simple visualization. Imagine a stretched sheet or mesh. When you place an object on it, the sheet bends under its weight. In the same way, spacetime bends or curves due to massive objects like planets and stars. The stronger the gravitational force of an object, the more it bends the spacetime around it. Interestingly, Einstein himself was not able to fully solve these equations. He only found an approximate solution for a specific case. The first person to solve them exactly was Carl Schwarzschild in 1916. He calculated how spacetime curves around a single mass. His solution helped scientists understand the concept of singularity, what happens if mass becomes infinitely dense. In such a case, the curvature of spacetime becomes so extreme that the region gets completely cut off from the rest of the universe. This is how scientists were able to theoretically prove the concept of black holes, and this happened more than 100 years ago. In fact, it was only in 2019 that scientists captured the first image of a black hole. So what I'm trying to say is that one solution of these field equations led to black holes, and we already knew about their existence theoretically almost a century before they were actually observed. And interestingly, these same equations also have another solution, wormholes. You might wonder how one equation can have multiple solutions, but think back to simple quadratic equations in school. Even a basic equation can have two solutions that both work. Einstein's equations are far more complex, so they can have many possible solutions. Wormholes are one of them, and their scientific name is the Einstein-Rosen bridge, named after Albert Einstein and his assistant Nathan Rosen, who worked together to describe this solution in 1935. Understanding wormholes is actually quite simple. They are basically shortcuts that connect two points in space-time. Let's first understand this in two dimensions to make it easier. Imagine a piece of paper with 2 points, A and B. If you want to go from point A to point B using the shortest path, what would that path be? A direct straight line connecting A and B, right? In two dimensions, there is no shorter path than that straight line. But if we take this two-dimensional surface and bend it into 3 dimensions, suddenly new paths appear. Imagine bending the sheet in such a way that points A and B come very close to each other. Now, instead of traveling the long distance along the surface, you can directly use the tiny distance between them. And if you create a path between these 2 points, like pushing a pen through the paper, you get a shortcut from A to B that is much shorter than the original path. This is exactly what wormholes do. In our three-dimensional world, it seems like the shortest distance from the Milky Way galaxy to the Andromeda galaxy is 2.5 million light-years. But if our three-dimensional space is bent through a fourth dimension, there might be a much shorter path connecting them. Now, imagining a fourth dimension is extremely difficult because we live in three dimensions, but you can understand it a bit better by comparing two dimensions and three dimensions. Let's take another example. Imagine a map of the world. If you want to fly from one major city to another faraway city, you might think the shortest path is a straight line on the map. But that's not actually the shortest route, because you're thinking in two dimensions. In reality, airplanes follow curved paths over the globe, which look longer on a flat map, but are actually shorter in three dimensions. In 1957, John Wheeler published a paper on Einstein-Rosen bridges and explained this idea using a simple analogy. Imagine an apple and a worm inside it. Instead of traveling along the surface of the apple, the worm goes through the inside and reaches the other side more quickly. In the same way, it takes a shortcut through space-time. That's where the term wormhole comes from. When you search for wormholes online, you'll often see diagrams showing two distant points connected through a tunnel. The idea is that space-time behaves like a fabric, and if there is an object with extremely strong gravity, it can bend this fabric so much that it folds onto itself. Just like folding a piece of paper, two distant points come close together, and a tunnel forms between them. This tunnel is a wormhole. It acts as a shortcut to travel from one galaxy to another. However, most of these visualizations are shown in two dimensions, which is not completely accurate. As mentioned earlier, wormholes would actually exist in higher dimensions. In reality, if a wormhole exists, it would likely appear like a spherical structure in space. As you travel through it, everything around you would look curved, and even when you look back, you would see objects moving farther away in a distorted, circular way. That's why the wormhole shown in Interstellar is considered quite realistic. But it's important to understand that wormholes are still just a theoretical concept. They come from solutions of Einstein's equations, and although scientists have created many models and visualizations, no one has actually seen a real wormhole. Scientists are not even sure if they exist, but if they do exist, they could act like time machines. Think about it, if you can travel millions of light years in just a few minutes, you are essentially reaching somewhere faster than light itself, which means you are also jumping through time. However, there are many practical problems. The first question is, how would a wormhole even form? It would require an extremely strong gravitational force. And where could such a force come from? Most likely from a black hole. Albert Einstein and his assistant Rosen theorized that only black holes might have enough gravitational power to open up these wormhole tunnels. Everything gets pulled toward a black hole, so matter would flow through this tunnel. But then another question arises, what happens on the other side of the tunnel? If there is another black hole on the other end, then there would be no way to escape. You would be completely trapped inside. In that case, a wormhole wouldn't be a passage, but a trap. So, for a wormhole to work as a shortcut, there must be something on the other side that is the exact opposite of a black hole, something equally powerful, but instead of pulling things in, it pushes things out, creating an exit point. And this is where the concept of white holes comes into the picture. White holes are also something that have been theoretically predicted through Einstein's field equations. Along with black holes and wormholes, white holes are another possible solution of these equations. So what exactly are white holes? Just like white is the opposite of black, a white hole is the complete opposite of a black hole in every sense. In a black hole, nothing can escape once it goes inside, not even light. But in a white hole, it's the opposite. Nothing can enter, and everything can only come out. This means a white hole would appear extremely bright, almost glowing white. The term white hole was first used by Igor Novikov in 1964. According to scientists, a white hole can be thought of as the time-reverse version of a black hole. Just like a black hole has an event horizon, which is a point of no return, once you cross it, nothing can escape. A white hole has a boundary of no entry. Nothing can go inside it, but anything inside can come out and interact with the outside universe. Even though white holes come from Einstein's theory, no one actually knows how they would form in reality. We understand how black holes form when a massive star collapses under its own gravity, but the reverse process doesn't really make sense physically. So whether white holes actually exist or not is still an open question among scientists. Some scientists believe that during the Big Bang, at the very beginning of the universe, everything might have come out of a massive white hole. Another idea is based on the work of Stephen Hawking, who suggested that black holes slowly evaporate over time due to radiation. When a black hole eventually disappears, what happens to all the matter and information inside it? In quantum physics, there is a fundamental idea called the no-hiding theorem, which says that information can never truly be lost. If it disappears from one place, it must exist somewhere else in the universe. So theoretically, if a black hole absorbs matter and information, it must release it somewhere, possibly through a white hole. Based on this idea, some scientists suggest that white holes might form when black holes die. However, we still don't have any solid evidence about how black holes actually end their life. On the other hand, many scientists argue that white holes cannot exist because they would violate the second law of thermodynamics. This law says that entropy or disorder in a system cannot decrease. For example, if you tear a piece of paper, the disorder increases, and you cannot perfectly restore it back to its original state. In the same way, black holes increase entropy by consuming stars, planets, and everything else, breaking them down into radiation. If a white hole existed, it would reverse this process and decrease entropy, which seems impossible according to current physics. Despite this, some scientists believe white holes might exist. In fact, in 2006, scientists observed a strange event using the Neil Gehrels Swift Observatory. On the 14th of June 2006, it detected a sudden burst of white light that quickly disappeared. This event was named GRB 060614. It was a gamma ray burst, which are extremely energetic explosions usually caused when a black hole consumes a massive star, but in this case, there was no evidence of any star, so some scientists suggested that this might have been a white hole. However, no similar events have been observed again, so white holes remain purely theoretical. It's important to remember that black holes were also once just a theory, but later they were proven to exist. So it's possible that white holes and wormholes might also be proven in the future. But even if wormholes are proven to exist, scientists still doubt whether humans would actually be able to travel through them. One of the most interesting developments related to wormholes came in 2015, when scientists managed to create a magnetic wormhole in a laboratory. Until now, we were talking about wormholes in terms of gravitational forces, but in terms of magnetic fields, scientists have already achieved something similar. Normally, a magnet has two poles, north and south, and even if you break a magnet into pieces, each piece still has both poles. But using special materials, scientists were able to separate the magnetic field in such a way that it behaved like it was passing through an invisible tunnel. In simple terms, the magnetic field entered through one end of the wormhole and exited from another, as if the 2 points were directly connected. This setup acted like a wormhole for magnetic fields. Although the device itself was visible, the magnetic field appeared to jump from one point to another. This magnetic wormhole was created using a high-temperature superconducting material called yttrium barium copper oxide, and the experiment was performed in a liquid nitrogen environment. Finally, even if wormholes are never proven to exist, it doesn't mean we won't find other ways to travel faster than light. There are several theoretical ideas, one of them being the Alcubierre drive, proposed in 1994 by physicist Miguel Alcubierre. The idea is to create a spacecraft that can travel faster than light by contracting space in front of it and expanding space behind it. In theory, this is also a solution of Einstein's equations. It will be very interesting to see what new ideas and solutions scientists come up with in the future and whether any of them can actually be turned into reality. I hope you guys liked this video and subscribe to this channel. Thanks for watching. I will meet you in the next video. Bye bye.